Now let's look at L'Hopital's rule, also known as the LH rule. So as we learnt about this earlier, this type of technique can be used only and only when we have these two type of indeterminate forms, which is 0 by 0 and infinity by infinity. So what we do in such type of x tends to a whatever, what we do in such type of questions, we simply differentiate the numerator and the denominator separately, and then we see if we can directly substitute and get our answer or not. Let's see if again it turns out to be in the indeterminate form, 0 by 0 or infinity by infinity. We can differentiate it once again to get our answer. So that is the only major thing that is there in L'Hopital's rule. As you can see, when can we use L'Hopital's rule? The limit results in an indeterminate form, which is 0 by 0 or infinity by infinity. The functions f of x and g of x are differentiable in the neighborhood of the point x is equals to c. Now for the time being, I would recommend you all to remember this point. When we study derivability or differentiability, that time you will understand what exactly this point means. The derivative of the denominator is not 0. Yes, of course, g dash x, g double dash x, or whatever is there in the denominator, it should not be 0. Because if it is 0, that means I have to make the numerator as well 0, so that it can become an indeterminate form again, and then I can differentiate again. Only one of them, only if the denominator is 0, that time I cannot say that my limit would exist, because it would turn into infinity. However, if f dash x is 0 and g dash x is, let's say, any other value apart from 0, that time I can say my limit exists and its value is 0. However, the vice versa is not the same. Again, the same thing that I've just told. Let's look at a question to understand this concept more. If x tends to 0, this exists and is equal to b. That means they've told us that this limit is existing. It is not indefinite or indeterminate. So first what we'll do is we'll first, of course, directly substitute x as 0. What do we get? 0 by 0. This is our indeterminate form. So we can use our LH rule. So let us simply differentiate the numerator and denominator. What do we get? In the numerator, we would have a minus 4e to the power x. And below, what are we going to be left with? We would have a e to the power 4x minus 1 plus ax 4 e to the power 4x. Now what I can do is, let me try and simplify this entire thing. Limit x tends to 0. Here I have a minus 4 e to the power x, e to the power 4x upon, here if I open this up, I would have a e to the power 4x minus a plus ax plus 4 ax e to the power 4x. Now if you can see, if I put 0 again, what would happen? In the numerator, I would have a minus 4. However, in the denominator, if I put x to be 0, it would become 0. That means you can see that the limit is coming out to be not existing. So how can I make this to be existing? Only and only if this becomes an indeterminate form again, so that I can differentiate it again, and then let's see if I can get my existing or finite value or not. So how can I say that this, I have to convert this into an indeterminate form? Determinate form. How? By saying that a is equals to 4. If a is equals to 4, that means this above would also become 0 and I would have 0 by 0. So I've gotten my first value of a, which is 4. That means a is equals to 4. Now I can substitute a is equals to 4 in this equation and then solve my question further. So what I do is limit x tending to 0. Now I'll put a as 4. I would have 4 minus 4 e to the power 4x upon 4 e to the power 4x minus 4 plus 4 4s are 16 x e to the power 4x. Now if you look at this entire equation and if you put x as 0, what are you going to get? It is again a 0 by 0 indeterminate form. So now I can differentiate this again by using my LH rule. So if I apply LH rule once again, what would this become? This would be minus 16 e to the power 4x divided by, this would become 16 e to the power 4x, minus 4 would simply get removed, plus I would have here 16 times of e to the power 4x plus 16x, 4 again gets multiplied, so this would become 64x e to the power 4x. I've directly written it down, you can check it by yourself. So from here, what can I say? If I take 16 common from below and as well as from the above, what am I going to get? Minus e to the power 4x upon e to the power 4x plus e to the power 4x plus, here I would have 4x e to the power 4x. Now let me simply replace x as 0. If I put x as 0, what would this become? E to the power 0, which is 1. So minus 1 upon, this would be 1 plus 1 plus 0, so this would be 2. So from here, my answer of limit is coming out to be minus half. And what have they told to us in the question? That the limit exists and is equal to b. So this value is equals to b. So b is my minus half and a is my 4. And what have they asked to us in the question? We have to find out a minus 2b. So what would this become? 4 plus 1, and our answer comes out to be 5. So this is how you have to solve questions of LH rule. Sometimes they might give you unknown variables in the equation like this one. So you have to create it in the indeterminate form so that you can differentiate it once again. So like how we did here, we assume that a is equals to 4 so that this entire thing becomes indeterminate form once again, and we can differentiate it once more. Had a been instead of 4, it had been, let's say, any other number, then we wouldn't have our limit existing. It would be indefinite or infinite. So that is why we did that. Now let's come to our Maclaurin series. This is also known as our Taylor series. Some people call it the Taylor series as well. So this was basically an equation, a general formula for all types of functions that was given by the scientist named Taylor or Maclaurin. So what is that equation? That equation, if I try to expand it, it can be expanded in this way. F of x is equal to f of 0 plus f dash 0 x plus f double dash 0 x square by 2 factorial plus f differentiated 3 times with x as 0, x cube by 3 factorial, and this goes on up till infinity. So the general term is written in this format. You can remember this general term. So let me take an example. Let's say if I was to open up sin x for you, my f of x is sin x here. Let's say my f of x is sin x. So as per the Maclaurin series, what can I say? F of x, this is equals to f of 0. What is sin 0? Sin 0 is 0. So I do not need to write it down. F dash x, what is my f dash x right now? Sin x can be differentiated as cos x. And now if I put x as 0, cos 0 is 1. So I would have x here again. F double dash 0, cos x differentiation gives me minus sin x. Minus sin x, and if I put x as 0, it would become 0 again. So that is removed again. F again differentiated. So now I had minus sin x, again differentiated would give me minus cos x. So from here I would have minus x cube by 3 factorial. And similarly this would go on and I would have this pattern formed. And this would go on up till infinity. So this is how any type of trigonometric, exponential or logarithmic functions are generally expanded using this series. And this comes in handy as now what you can do is whatever trigonometric identities and all those identities, standard limits that we studied in the starting of the lectures, you can try to prove all of them using these series and expansions. Now these are certain common series expansions that you must remember because it becomes easier for you to solve questions. One is the exponential, e to the power x opens up in this format, sin x opens up in this format, cos x opens up in this format, 1 plus x to the power n. Here we are considering this is a type of a binomial expansion. So this is a binomial expansion. So it expands this way, logarithmic ln 1 plus x, we get x minus x square by 2 plus x cube by 3, and it goes inverse tangent. So again, you can find out all the functions that you want, their expansion based on this series. So you must remember this series or its general term mostly. These three are the most basic and the most important ones, as well as this one. So try to remember these 4 expansions by heart so that it becomes easier for you to solve question. Now let's look at this question as well. Limit x tending to 0, e to the power ax minus cos bx minus cx e to the power minus cx by 2. Simply, what is the first step that we are going to do? We are going to put x as 0. As soon as we put x as 0, we can see it is a 0 by 0 indeterminate form. So since it is an indeterminate form, and by looking at this, what can we see is that apart from differentiating or using the LH rule, what can we do is we can simply expand this equation. If we try to expand this equation and we remove this 1 minus cos 2x by dividing it by 4x square, we can get something out of it. So let us try to solve it in that way. We get limit x tending to 0. How does e to the power ax open up as? We had studied ex opens up as 1 plus x square by 2 factorial. So let us write it down in this way. E to the power x would open up as 1 plus ax square by 2 factorial plus ax cube by 3 factorial, and this would go on. Minus, how does cos bx open up as? Cos x opens up as 1 minus x square by 2 factorial plus x to the power 4 by 4 factorial. 1 minus x square by 2 factorial, so bx square by 2 factorial plus bx to the power 4 by 4 factorial minus, and this would go on up till infinity, minus, what do we have here? Cx by 2 into e to the power minus cx. Again, let me open this up in the same format. This would become 1 plus minus cx plus minus cx square by 2 factorial plus minus cx cube by 3 factorial, goes up till infinity. Now this entire thing is divided by 1 minus cos 2x. What do I do is I divide this by 4x square and I multiply a 4x square here. So this entire term, what does this become? This becomes half. That means 2 gets multiplied on top. So I would have a 2 multiplied out here. Limit x tending to 0. Now let me try and cancel out stuff from here. This one and this one can get cancelled out. I can see there is an x square here. So if I try to remove x square from the terms, what am I going to get? First, let me write down the x coefficient above. What are the x coefficients left out? A, from here there is nothing. From here I would have minus c by 2 plus x square. What are the coefficients of x square that are going to be left out? A square by 2 factorial. From here I would have plus b square by 2, and from here I would have plus c square by 2. Now again, I'm not writing down all the x cube coefficients, because of course x cube, x4, all these things will be 0, because down here I have 4x square. X square can cancel out x square only. So from here I know that x, this term, I need to make it to 0, because if I do not make it to 0, this is going to create problems for us and we cannot maintain our entire thing. So what we used to do for infinity, we used to make all the larger powers to be 0. Here what we are doing is we are making all the lower powers to be 0, because x is tending to 0. So from here what do we get? We must say that a minus c by 2, this should be equal to 0. That means 2a is equals to c. This is one of the equations that we've gotten. Now what I can do is simply this 2 would cancel out this 4 here twice. X square and x square would cancel out each other, and from here what would we be left with? Our limit x tends to 0, the entire solution. Let me write it down directly. So it would become a square half into a square by 2 plus b square by 2 plus c square by 2. This is my final solution, and this value is equals to 17 as they had told to us in the question. So this becomes a square plus b square plus c square. This is equals to 2 and 2 gets multiplied and gets here, so it becomes 58. And we know that c is equals to a, so let me replace c by a. What am I going to get? A square plus b square plus 4c square, 58. So here I have 4a square. 5a square plus b square, this is equals to 58. What is the value they were asking in the question? They were asking us to find out 5a square plus b square. This is what we are getting as 58. Sorry, this would become 68. So 68 becomes my answer. So I hope now this might have seemed a bit confusing for you all, but if you try to solve it by yourself, it would become very easy for you, because the only thing that I did in this entire equation was I expanded my terms and I removed all the terms that had powers which were greater than the power of the denominator. Since x is tending to 0, so all those powers which are greater than 1 in the denominator, they would become 0. So I ignored all those powers. I removed those. I took only x and x square, and I had to make x as 0 because they were two separate terms. I couldn't cancel out x square. So I had to make that term 0. So a minus c by 2 became equal to 0, and from there we got our solution. So basically when x tends to 0, it is completely the reverse of what we used to do for infinity. So that is how you get your answer.